In the spring of 1993, three engineers walked into a Denny's restaurant on the corner of Capitol and Berryessa in East San Jose, ordered bottomless cups of coffee, and began sketching the architecture of the future on paper napkins. They had $40,000 in the bank, no customers, and a vision that most semiconductor veterans would have called delusional. One of them, a 30-year-old Taiwanese immigrant named Jensen Huang, had spent his teenage years washing dishes at that exact same Denny's. He would later joke that the restaurant was his first company. What they built in that booth would eventually become the most valuable corporation on earth, a firm that now powers everything from the artificial intelligence behind your web searches to the supercomputers training the next generation of autonomous vehicles. But in 1993, the personal computer could barely render a smooth two-dimensional sprite, and the idea that it would need a dedicated engine for three-dimensional graphics seemed like a solution in search of a problem. The problem, as it turned out, was enormous. The gap between professional graphics workstations costing tens of thousands of dollars and consumer PCs was vast, and that gap was the opportunity. Jensen Huang had earned his electrical engineering degree from Oregon State University and his master's from Stanford, and he had spent time designing microprocessors at AMD and running a business unit at LSI Logic. His co-founders, Chris Malachowski and Curtis Priam, were engineers from Sun Microsystems. Together, they incorporated Nvidia on January 25, 1993, choosing a name derived from the Latin word Nvidia, meaning envy. They were fabless from day one, meaning they designed chips but owned no factories, a lean model that would later become standard in the industry, but was still relatively uncommon at the time. Their first product, the NV1, shipped in 1995 and was a commercial disaster. It used a non-standard rendering approach called quadratic texture mapping, while the rest of the industry was standardizing around conventional triangle-based rendering. Developers overwhelmingly preferred the competing 3DFX Voodoo card. Nvidia had to lay off most of its employees and was down to its last few months of runway. Huang would later describe the failure with characteristic bluntness. Their approach was just different enough to be incompatible, but not different enough to be better. The turnaround came with the Riva 128 in 1997, a chip built on industry-standard triangle, rendering that sold over 1 million units in its first 4 months and pulled the company back from the brink of bankruptcy. The Riva 128 was manufactured by SGS Thomson on a 350-nanometer process, not by the Taiwanese foundry TSMC that would later become synonymous with Nvidia's production. That partnership began in 1998 with the Riva TNT, after Huang had mailed a letter to TSMC's founder, Morris Chang, a correspondence that would blossom into one of the most consequential relationships in modern semiconductor history. By 1999, Nvidia had gone public and released the GeForce 256, which the company marketed as the world's first GPU, or graphics processing unit. The key innovation was programmability. Previous graphics chips were fixed-function accelerators, hardwired to perform specific rendering tasks. The GeForce 256 added programmable shaders, meaning developers could write code that ran directly on the chip. This programmability would prove far more consequential than anyone realized at the time. Microsoft, whose DirectX architecture had nearly sidelined Nvidia in its early years, chose the GeForce to power the original Xbox. The company that had nearly died in 1996 was now a dominant force in PC gaming, a position it would hold for decades. But the real bet came in 2006 when Nvidia launched CUDA, short for Compute Unified Device Architecture. CUDA was a platform and programming model that allowed developers to use GPUs for general-purpose computing tasks, not just graphics. The idea was met with widespread skepticism. GPUs were designed to render pixels, not to crunch scientific data or train machine learning models. Huang and his team believed otherwise. They saw that the massively parallel architecture of a GPU, with its hundreds or thousands of cores working simultaneously, was ideally suited to the kind of repetitive mathematical operations that characterized many computational workloads. CUDA was a long-term investment that cost billions of dollars and generated little revenue for years. It was, in effect, a bet on a market that did not yet exist. That market arrived on September 30, 2012, at the European Conference on Computer Vision in Florence, Italy. A team from the University of Toronto led by Alex Krzyzewski, along with Ilya Sutskever and their advisor Geoffrey Hinton, presented the results of a deep convolutional neural network they had trained to recognize images. Called AlexNet, it had won the ImageNet competition by a margin so staggering that it effectively ended the debate about whether deep learning was viable for real-world applications. AlexNet achieved a top 5 error rate of 15.3%. The runner-up scored 26.2%. The neural network had been trained on 2 Nvidia GTX 580 GPUs using the CUDA platform, because the model was too large to fit on a single card. In the audience that day was Yann LeCun, who would later win a Nobel Prize for his own work on neural networks. He stood up and called AlexNet an unequivocal turning point in the history of computer vision. What almost nobody in that room fully grasped was that AlexNet had just validated not only deep learning, but Nvidia's entire strategic direction. The GPUs that gamers use to render more realistic explosions and smoother frame rates were suddenly the most important hardware in artificial intelligence research. The convergence was almost accidental. Fei Li had spent years building the ImageNet dataset, a collection of over 14 million labeled images that most of her colleagues had initially dismissed as absurdly large. Geoffrey Hinton had spent decades promoting neural networks in the face of near-universal skepticism, and Jensen Huang had spent billions building a parallel computing platform that most of the industry had ignored. When these three threads came together in 2012, the result was the modern AI revolution. Within months, Google acquired Hinton's team for $44 million. Ilya Sutskever would later co-found OpenAI, and Nvidia, valued at less than $10 billion at the time, began a trajectory that would eventually make it the most valuable company in the world. The years that followed saw the deep learning boom accelerate. Every major technology company began building AI research labs. Cloud providers like Amazon Web Services, Microsoft Azure, and Google Cloud started offering GPU instances for machine learning workloads. Nvidia's data center revenue, which had accounted for roughly 5% of the company's sales in early 2014, began to climb. By fiscal year 2025, which ended in January 2025, that figure had flipped almost entirely. Data center revenue reached $115.2 billion, up 142% from the previous year, and now constituted over 90% of Nvidia's total business. The segment had grown roughly 300-fold in just 12 years. Total company revenue for fiscal 2025 hit $130.5 billion, more than double the prior year. Operating income rose 147% to $81.5 billion. Net income reached $72.9 billion. In the final quarter alone, the company generated $39.3 billion in revenue and $22.1 billion in net income, including $11 billion from the new Blackwell architecture chips in their very first quarter of mass shipment, the fastest product ramp in the company's history. This financial explosion was driven by a structural reality. Nvidia had built a moat that was part hardware, part software, and part ecosystem. The CUDA platform, after nearly 2 decades of refinement, had amassed over 5 million developers worldwide. Competitors could design chips with similar raw performance, but they could not replicate the software libraries, the optimization tools, the research papers, the university courses, and the institutional knowledge that had grown up around Nvidia's stack. When an AI researcher writes a model in PyTorch or TensorFlow, the code that actually executes on the hardware is almost certainly calling CUDA kernels under the hood. When a startup trains a large language model, it is almost certainly running on Nvidia GPUs. Industry estimates suggest that over 90% of all AI model training in the world happens on Nvidia hardware, and the company accounts for roughly 85% of the global market for AI chips. Nvidia's dominance is not merely a matter of silicon, it is a matter of vertical integration. In 2019, the company acquired Mellanox, an Israeli provider of high-speed networking hardware, for $6.9 billion. Mellanox's InfiniBand interconnects were already used in more than half of the world's fastest supercomputers, and the acquisition gave Nvidia control over the data center network layer, not just the compute layer. Modern AI training runs require thousands of GPUs working in concert, and the speed at which those GPUs communicate with one another is often the bottleneck. By owning both the chips and the interconnects, Nvidia could optimize the entire stack in ways that no competitor could match. The company attempted to extend this vertical integration even further in September 2020, when it announced a $40 billion acquisition of ARM Limited, the British firm whose chip designs power the vast majority of smartphones and an increasing share of servers. The deal would have been the largest in semiconductor history, but it faced regulatory opposition on multiple continents. The United States Federal Trade Commission filed an administrative complaint in December 2021. The United Kingdom's Competition and Markets Authority opened a Phase 2 investigation on both competition and national security grounds. The European Commission launched its own in-depth probe. China's State Administration for Market Regulation had barely begun its review when, on February 7, 2022, Nvidia and SoftBank jointly terminated the agreement, citing significant regulatory challenges. Nvidia recorded a $1.35 billion acquisition termination charge and retained a 20-year ARM license, but the deal was dead. No regulator had ever issued a final order blocking it. The company had simply walked away rather than fight a multi-front war it was unlikely to win. The failure to acquire ARM did not slow Nvidia's momentum. If anything, it clarified the company's focus. In March 2024, Jensen Huang took the stage at Nvidia's annual GPU Technology Conference, an event that industry observers had begun calling the Woodstock of AI, and unveiled the Blackwell architecture. Named after the statistician David Blackwell, the new generation of data center chips contained 208 billion transistors manufactured on TSMC's 4-nanometer process. The flagship B200 GPU delivered 20 petaflops of compute in certain precision modes, roughly 2.5 times the performance of the prior generation H100 at similar power consumption. But the more radical product was the GB200, a superchip that combined two Blackwell GPUs with a Grace CPU on a single substrate, connected by NVLink at speeds that eliminated the traditional bottleneck between processor and accelerator. A full GB200 NVL72 system, liquid-cooled and drawing 120 kilowatts per rack, connected 72 GPUs and 36 CPUs into what effectively functioned as a single massive processor. The scale was staggering. These were not graphics cards anymore. They were industrial infrastructure, the engines of what Huang called the new industrial revolution. The demand was insatiable. Microsoft alone purchased 485,000 Hopper generation AI chips in 2024, double the amount bought by its closest rival, Meta. Cloud providers raced to deploy Blackwell systems across their global regions. Nvidia announced it would serve as a key technology partner for the Stargate project, a $500 billion initiative to build AI infrastructure in the United States. The company's annual GTC conference in 2025 drew 7,200 attendees in person and hundreds of thousands online, representing over 10,000 companies and more than 400 startups from roughly 100 countries. Jensen Huang, now in his early 60s and worth well over $100 billion, had become the longest-serving CEO in major technology, having led the same company for over 32 years through near bankruptcy, market crashes, and multiple technological revolutions. His management style remained as unconventional as ever. He maintained over 60 direct reports, almost all of them engineered, and held no scheduled one-on-one meeting. Problems were attacked collectively in open forums where the memory expert, the networking expert, and the GPU architect were all in the same room, listening to each other in real time. He had repeatedly declined to hire a chief operating officer, comparing the company to a race car that he needed to know how to drive himself. Yet dominance on this scale inevitably breeds opposition. In December 2024, China's State Administration for Market Regulation opened an antitrust investigation into Nvidia, alleging that the company had violated commitments made during its Mellanox acquisition regarding fair competition and technology access within China. The probe came amid a broader technological Cold War between Washington and Beijing, with the United States imposing increasingly strict export controls on advanced semiconductors to Chinese entities, and China retaliating with investigations of its own. Nvidia had already been forced to create cut-down versions of its chip, such as the H20, to comply with U.S. export restrictions while still accessing the Chinese market. The regulatory scrutiny was not limited to China. The European Union, the United Kingdom, and the United States had all shown growing concern about the concentration of AI compute power in a single company's hands. Competition was intensifying as well. AMD, under the leadership of CEO Lisa Su, had made significant inroads in data center and AI applications. Intel, despite years of manufacturing struggles, was pushing its own accelerator chips. More threatening in the long term were the custom silicon efforts by Nvidia's own largest customers. Google had developed its Tensor Processing Units, or TPUs. Amazon had Trainium and Inferentia. Microsoft had its Maya chips. These were application-specific integrated circuits, or ASICs, designed for narrow AI workloads rather than general-purpose GPU computing. They could not match Nvidia's flexibility, but for the massive training runs that consumed the majority of data center budgets, they offered a plausible alternative. If the hyperscalers could train their largest models on their own chips, Nvidia's growth might eventually plateau. There were other vulnerabilities. Nvidia designed its chips but manufactured almost none of them. Roughly 90% of its leading-edge production went to TSMC, the Taiwanese foundry that itself manufactured roughly 70% of the world's most advanced logic chips. Any disruption to Taiwan, whether geopolitical, seismic, or logistical, would send shockwaves through the entire AI supply chain. The company's Blackwell systems were so power-hungry that some data centers required complete electrical retrofits to support them. A single GB200 NVL72 rack drew as much electricity as a small neighborhood. As AI models grew larger and inference workloads surpassed training in total compute demand, the energy constraint would only tighten. Companies delivering meaningful efficiency breakthroughs, whether through new chip architectures, advanced cooling, or algorithmic optimizations, could erode Nvidia's position. But if Nvidia had a defining trait across its three-decade history, it was the willingness to bet on transitions before the rest of the industry saw them coming. The company had bet on 3D graphics when PCs were still primarily business machines. It had bet on programmable GPUs when fixed-function accelerators were cheaper. It had bet on CUDA when parallel computing was an academic curiosity. It had bet on AI when deep learning was a fringe research topic. Now it was betting on what Huang called physical AI, the application of generative models and reasoning systems to robotics, autonomous vehicles, and industrial automation. The company had built platforms for self-driving cars, humanoid robots, and digital twins of factories and cities. These markets were still tiny compared to data center AI, but they followed the same pattern. Nvidia was building the infrastructure years before the applications matured. The through line from that Denny's booth in 1993 to the trillion-dollar colossus of today is a single, stubborn belief. Accelerated computing, the idea that specialized processors could outperform general-purpose CPUs for specific workloads by orders of magnitude, was not just a product strategy. It was a theory of how the entire computing industry would evolve. For most of Nvidia's history, that theory looked wrong, or at least premature. The company survived multiple near-death experiences, outlasted dozens of competitors, and endured years of Wall Street skepticism about whether its gaming business could ever justify its valuation. Then, in the span of roughly a decade, the world caught up to the vision. The algorithms that power modern artificial intelligence are almost perfectly suited to the parallel architecture that Nvidia had spent 30 years refining. The result is a company that does not merely participate in the AI revolution, but provides the physical substrate on which it runs. Every time you ask a large language model a question, every time a recommendation engine suggests a product, every time a self-driving car processes a frame from its cameras, there is a high probability that the computation is flowing through silicon designed in Santa Clara by engineers who once worried whether they could make payroll. What makes this story more than a tale of corporate success is the structural position Nvidia now occupies. It is not just a technology company, it is a bottleneck in the global economy. Nations are crafting industrial policy around access to its chips. Energy grids are being reconfigured to power its systems. The largest companies in the world are making capital expenditure decisions that depend on its product roadmap and manufacturing capacity. The future of medicine, materials, science, climate modeling, and defense all run to a significant degree on Nvidia hardware. That concentration of power brings risks. Monopolies stifle innovation. Geopolitical dependencies create fragility. It has become infrastructure as essential to the modern economy in its own way as railroads, electricity, or the internet itself. And the three engineers who sketched it all out over bottomless coffee in a San Jose diner could not possibly have known what they were starting.